Hello, everyone. Today we're talking to Steve Collins, an associate professor at Stanford University in the Department of Mechanical Engineering. Steve holds the dubious honor of being my PhD thesis advisor. Steve is known for a lot of things, ranging from early days of building highly efficient walking robots to today where he's exploring all sorts of interesting human-in-the-loop paradigms to control wearable robotics more effectively. And there's lots more. Well, without further ado, welcome Steve Collins. Hi, Steve.
Hey, Josh. How's it going, man? Good to see you.
Good. Yeah, long time no see. Thanks for joining the podcast.
Yeah, my pleasure. Good to be here.
So I'd like to start off by asking you to provide our audience with a 30,000-foot view of all the things you've done so far in your academic career.
Sure. Well, I think you hit on the high points in your intro there. So I got my start as an undergrad, joining projects to design really energy efficient walking robots based on passive dynamics. And then as a PhD student, I learned how to apply those ideas to human walking and biomechanics and started to work on designing prosthetic limbs. And then as a professor for the last few years, I've been 13 years now, actually. Wow. We're getting older, Josh. And then we're working on new methods for designing prosthetic limbs and exoskeletons, really a response to some of the failures of the projects in my PhD based on emulation and human-in-the-loop optimization. And hopefully we'll dig into some detail on any or all of those topics.
Absolutely. Yeah. When I think of you, I think of your sort of obsession with energy efficiency. And I think this is like it pervades all of your work. And I think it's a profound concept. I'm wondering if you could kind of explain how this has captured your interest, obviously in the early days with robots, but today in helping people move more effectively. Is it the kind of the keystone in your opinion?
That's a great question. So why did energy efficiency capture my interest? I guess it's a pretty fundamental thing, right? You've got sort of your first law of thermodynamics. Unless we have some kind of nuclear reaction happening, energy is conserved, and so it's hard to get around. This is one of those constraints in life. So using less energy to complete a task, always better, everything else being equal, say. And it's proved a challenging problem in robots and in assistive devices, which is also, to me, appealing. It's an objective measure that's really hard to improve on. But I guess also, in my case, part of the reason I got so focused on energy costs, especially earlier in my career, is just where I started, which was in these walking robots. So, I was an undergraduate student working in Andy Arena's lab at Cornell, and he showed these videos of passive dynamic walking robots in a dynamics course that I took, for my required undergraduate degree. And I was just floored by these movies of these robots moving, no motors, no computers, but this really fluid human-like movement, and using just a tiny amount of energy harvested from gravitational potential energy as they walked around. And for that project, energy efficiency was the big goal. It was one of the main selling points of that approach to getting a robot to walk. And so, right from the outset, we were very focused on trying to develop the most energy efficient walking robots in the world. And to get there, we made a lot of sacrifices in other objectives that you really care about, like robustness. These things fell down most of the time that I tried to get them to walk. And speed, they're quite slow compared to humans, but they were very, very efficient. And, as I started to try to apply those techniques and ideas to devices that would be more directly beneficial to humans, walking robots may someday, you might find them in our houses helping us out. There might be caretakers for older people and delivery robots and things. But for me, the more compelling way that this technology could really help people is by improving mobility for people with disabilities. So, and that means rehabilitation robots, assistive robotic devices like exoskeletons and prosthetic limbs. So we started, by trying to make prosthetic devices that reduce energy consumption, because fatigue is a real problem for people with amputation. But of course, the more you get into the field, the more people you talk to, and the more clinical experts you talk to, the more you see that, yes, this is an important objective, but it's just one of many important objectives. And some goals are probably more important, like comfort at the residual end for people with amputation. And there are many that are equivalently important: speed and balance. So as we've gone along, we've started to address more and more of these objectives. And, the long-term goal is to develop devices that simultaneously improve performance across a large set of objective measures of performance and satisfaction, with the right balance struck between them, perhaps depending on the user and their environment, things like that.
Makes sense. Yeah, when I think your average person who's not engaged in this field thinks of energy efficiency, you might think of global warming and the need to make cars more efficient or power generation more efficient, and kind of stave off concerns about a warming climate. In wearable systems, I don't know if that's the case, but how do you see this? Presumably the logic has something to do with people today being unable to perform certain activities and experiencing, as a result, a diminished quality of life. Is it that if we had more efficient wearable robots, they'd be more likely to be active and live happier, healthier lives?
Yeah, well, yeah, definitely. So the first point about reducing, say, carbon emissions, I think does apply to some degree. And some of our more recent work has been on new types of actuator that can replace motors that are really energy efficient. And we have some work that's under review at the moment. I should probably get into too many details, but in demonstrating this sort of general purpose actuator that can save a lot of electricity, that could potentially apply to, say, industrial assembly line robotics applications and self-driving electric cars and things like that, where actually there is some better use of renewable electricity generated by solar or reduced use of fossil fuels. But mostly the reason they want to save energy in the kinds of applications we work in, is wearable and mobile robots, is to be able to go farther with the same size battery, or to have a smaller, cheaper, and less heavy battery in your system. And that is a real limitation. There have been some careful user studies of early phase prosthetic limbs suggesting that range of the device, the amount of walking you can do before you have to recharge the batteries, is a serious factor that influences adoption or lack thereof of those devices. So if we could get our prosthetic limbs to run all day and let you walk as much as you want without needing to recharge or swap batteries, that would meaningfully improve the user experience.
Interesting. This is anecdotal, so take it with a grain of salt. But I was reading an article recently about the sort of energy impact of battery-powered scooters. And whoever wrote this article had the viewpoint that actually they had a harmful impact in terms of global emissions, because people were not switching from more sort of energy expensive modes of transit to the scooters. They were switching from less energy expensive modes of transit to the scooters. So basically, they weren't switching from cars to scooters, they were switching from walking to scooters. It strikes me, though, that this could be one of the big opportunities with wearable devices, because unlike a scooter, which is this big thing you need to store somewhere and charge, and you can't take it upstairs and yada yada, the wearable robot could eventually be part of your clothing.
You're right. The net effect of any new technology. So let's say you make some device way more energy efficient. Does it then use less energy? It does if it's used in exactly the same way, but not if the use changes, which always does happen to some degree. So yeah, if we make mobile robots or assembly line robots way more energy efficient, and as a consequence, people choose to have them operate more often, then you could increase energy consumption. And there's a close parallel in humans, of course, that could actually be beneficial, which is, the first thought of many people when they hear, oh, you're making these devices to reduce the effort of walking, reduce energy consumption of walking. Don't we have an obesity epidemic in this country? I mean, and that can just make people fatter. That's a big problem. And it could happen. So if people's activity stayed exactly the same and you make every step cost less metabolic energy, then of course people will expend less energy and get less exercise. But just in the way that, these changes, these scooters and other new tools in our lives change our behavior, if we make each step of walking a little bit easier, it may well be that people take a lot more steps during the day, choose to be more active, and they could end up expending a lot more energy over the course of the day. There was a fun study from UC Boulder. I don't remember the full author list, but I remember Roger Crom was part of the study, where they gave people bikes. They gave them either electric assist bikes or just regular pedal powered bikes. And they measured the amount of cycling people did in a week, and they sent them home 2 or 4 weeks, and they were instrumented so they could tell how far they'd gone. And people, I think it was like 4 times as much cycling was done by the people with the e-assist bikes. Unfortunately, they did not measure the amount of exercise that people got from that activity, but depending on the level of assist, it could easily be that people got a lot more exercise from cycling in the assisted case than in the unassisted case. And so we still don't have the exoskeleton and prosthesis technology we need to do that study for those kinds of devices. We need like really reliable devices that consistently make a large improvement in the effort of walking to see what the net effect is on energy expenditure and activity. But I'm of the camp that expects, my hypothesis is that people actually will be more active when using these devices, and there'll be a net health benefit. But it remains to be seen in some, well-controlled.
I think it's good to be optimistic. I'm glad we went down this path, because I think these are big ideas that we all need to keep in mind to kind of help us rationalize and question, what this field is all about, what we're hoping to achieve. We've been talking about devices with batteries, but a big tenet of your work has also been building clever passive mechanisms. How do you think about that choice that you as the designer have to make, whether to bring in power or to sort of avoid the need for motors and batteries?
Yeah, well, I mean, you could think of it as sort of one end of the spectrum, right? The most energy efficient robot is one that uses no electricity at all, and it's a kind of a fun space to explore and see, what can you do without motors and batteries. And it is sort of a step change because if you can get to zero, then your system can become a lot simpler and cheaper, and potentially, if it's nice and elegant and so on, it could be more reliable in some ways. But when you don't have any computer-controlled inputs to the system, the range of complexity of behaviors that can be exhibited does decrease quite a bit. The idea of mechanical intelligence has had a following in our fields for a few decades. And there are some good examples. Passive dynamic walkers are one. There are some cool, spring mechanisms that do self-balancing for gravity cancellation. You can make arguments about mechanical intelligence built into muscle physiology. The passive responses of muscles to changes in length or velocity. That's sort of somewhere at the border between passive and active. But it's just, your mechanism has to get very complex to have anything like the level of sophistication you can encode into a computer-controlled, software-controlled device. So you should expect to have a lot better versatility and robustness in those kinds of systems.
The ideal paradigm where you can ask these questions, free from the constraints of needing to build a portable system, you can ask, questions about what the ideal torque profile looks like and what sort of mechanisms or motors might you need to achieve that. You, of course, envisioned off-board actuated wearable robots long before Humotech even existed. And, we built the first systems together in the lab, building what became today the Caplex system. Yeah, and you've done all sorts of interesting things, built crazy custom end effectors and advanced algorithms. There's so much. I'm wondering if you could kind of share maybe some of the highlights for you, the phases of work where you used emulation to kind of unlock the next big thing.
Yeah, there's a lot of, so I want to mention just quickly that the sort of core idea here was really, it came from bouncing ideas around in the lab. I was in our closed lab back in the aughts with people like Peter Adamczyk and Greg Sawicki and Sean O'Connor. And I think it was Peter that said, what we really need is superfoot. That was what he called it. A prosthesis that can do anything. Then we can test all the ideas that we want to test. And that really stuck with me through I did a postdoc in the Netherlands with Martijn Wisse and met Herman van der Kooi and his group, and they had these tethered exoskeletons that were used a little differently than the way we're using these emulators, but there's still, some features of that approach that resonated and seemed like, oh, that could really work well. And I think eventually this distilled down to that, but by the time I was starting, with you as my first PhD student back at Carnegie Mellon in 2010, the idea was that the sort of philosophy behind this approach is that humans are really complicated. And so it's very difficult to predict how they're going to respond to some wearable device. And we need to accept that, embrace that fact. And the first implication is that our ideas for designs that are going to help people will probably fail most of the time. And so instead of putting a lot of effort into a beautiful embodiment of our intuition-based or simple model-based design for an assistive device, we should, and then we'll find out that it fails, we should instead make systems that are really versatile, that allow us to try many, many different ideas for assisting people without building new hardware. And that's what emulators are. It's designing for versatility rather than designing for high performance in one specific mode. So if you have that sort of virtual reality system where you can get that physical experience of interacting with lots of devices, then your odds of the space of possible devices, including something that is beneficial, go way up. And that's especially true if you have tools for searching the space systematically, like human in the loop optimization. And so I guess the sort of highlight of, and on my lab for this approach would be our development trajectory for ankle exoskeletons. So we started out with emulation, and we did some parameter studies and hand tuning and got, some modest improvements in energy economy compared to, walking with the device turned off. This was, Rachel Jackson's work back in the day. And then we introduced human loop optimization. Sean led that work in our lab and got these much larger improvements, the benefits of assistance with the ankle exoskeleton went way up. And we continued to refine the work, looking at the effects of training. Pete Pognancy led that thrust in our lab. And, with bilateral devices, and eventually we felt like, okay, we really have it down. We've got a behavior of these ankle exoskeletons that delivers these large improvements in energy economy. Now, can we turn that into an untethered device with similar capabilities? And the answer is yes. Actually, that's fairly easy. That was Patrick Slade did that work here at Stanford, and it was about, I don't know, a little less than a year to go from the design specifications we got with the emulator to an untethered device that embodied them with, it's lightweight and ran as long as we needed to run. And then taking it one step further, the emulator allowed us to collect more easily than possible with an untethered device this large set of data that we could then learn models from, and that were embeddable into this untethered device where we don't have all the laboratory equipment for measuring energy cost and so on, so that we could even do the optimization out in the real world with an untethered device. So that, emulation's just central to that process, and it was the secret to our success in this combination of emulation and optimization. And that device to me is like, yeah.
Could you speak a little more to directly to the point about how collecting data with the emulator enabled portable device to be developed more effectively? Because I think at a fairly high level, this makes intuitive sense to people. But exactly how you baked that cake, I think would be interesting to describe a little more.
Sure. Yeah. Well, to be honest, we did not set out in the experiments we performed, where we collect a lot of data, with the intention of collecting training data for models. It was just serendipity that we started to do some machine learning work in the lab, and hey, we had this big training data set. We always we knew that that the data set was important, and that people would be able to go into it to address questions they might have about how people use exoskeletons, ankle exoskeletons, and how they learn to use them. But it turns out it also was a great data set for learning a model that can classify different exoskeleton behaviors to see which one is better in terms of improving energy economy for the user. But yeah, so why are emulators good for gathering data for learning models? And first, it's important to say the main problem we have in applying ML techniques in prosthetic limbs and exoskeletons is that we don't have enough training data, right? That's our main obstacle. If you can just scrape the internet, then you can develop these billion parameter models of natural language, but we just don't have anything like that. So a big challenge for our field right now is to try to get those data sets so we can learn models of, just how the nervous system responds to different environmental conditions, how it learns how to use things, and specifically how people respond to different wearable devices. That category, I think emulators are a great key tool because, if anybody who's worked with a product like device knows it's just, there's all this additional overhead. You've got this specialized thing. Everything's right on the edge of its engineering tolerances and safety factor. And you're constantly changing out batteries and having motors overheat and all that stuff. But with this big box of motors sitting over there on the other side of the room and this big stack of computers, that stuff just works. Especially you remember the full trajectory of this hardware in our lab back when you started on this stuff. The research tools we developed were not the most reliable pieces of hardware, which is always the case, right? But now, now that you have this great company, Humotech, that's engineered these great, really bulletproof solutions, and that's what we use in the lab, and that's a real asset. So it just works. We've been using those Humotech systems for 6 years now, and nothing is broken so far. It's like, and we've done hundreds and hundreds, probably a few thousand hours of data collections with exoskeletons, various exoskeletons and prosthetic limbs, without a breakdown.
It's
to get that
Thanks,
training to
Steve.
yeah. Well, it's true. I'm allowed to be a little proud of my my poor PhD student out there doing awesome stuff in the world. But yeah, so with in the case of the training data set we used for the untethered exoskeleton study, that was several thousand different exoskeleton conditions, and I think it was 120 or 150 hours of data collections in the laboratory, and it's just the overhead for doing that with a tethered laboratory-based system is just way.
So for the engineers that are engaged in the R&D that we're talking about, I feel like I generally have a fairly easy time kind of describing the merits of this approach. But to those who are kind of viewing the work from afar or at a higher level, speaking about the value of emulation for the industry, I feel like one of the key missing data points is commercial success of devices developed from R&D out into the real world using emulation. I'm curious for your thoughts on where your portable ankle exo is going. Maybe we should start another company. And B, kind of, how do you see this proliferating? Humotech has worked hard in kind of building these systems. We've built over 25 of them now, but it's a slow to evolve market.
Well, totally. And I'm appreciative of the choir here, of course, but I do think it has a lot of value. So maybe the first thing to say is that the name of the game early in the development of a new assistive device is versatility in the hardware. So now emulators are not the only way to get there, right? You can imagine different ways of having a reconfigurable or highly versatile system. There's even passive devices where you just like go and tune a few parameters. And if, let's say you're only interested in passive prosthetic limbs or something, you could have a manually adjustable device. But an emulator, it makes things a lot easier and allows you to explore this bigger space of control strategies. So if we're talking about research and development, I mean, I will not be starting a project for a robot that's going to interact with a human that doesn't start with some emulation base. I can tell you that in my career. If you want to explore passive devices, you emulate the passive device with a robotic system, and then you can capture a much wider range because there's all kinds of crazy, interesting mechanisms and components that you could put into a passive device. And it would just be really annoying to be trying to come up with a hardware system that allows you to swap things in. And then you could also see this being used for prescription. And I've been following your work in this area with a lot of excitement and anticipation. I'm eager to see what you and the VA team have come up with here. But it seems like a great application to have people be able to try, get that experience of using lots of different kinds of device while using one tethered emulator. And then after that, you have objective clinical evidence that there will be some benefits to the particular device that they end up being prescribed, and the best settings and configuration of that device. And you can imagine a similar thing that you can see that in like a clinical setting or in a commercial setting. But as you say, a challenge at the moment is just that we are pretty early in the trajectory of wearable robotic devices. There aren't examples of really widely used products out there yet. But I think that the main reason that's true is because we just haven't had devices yet that do deliver a big enough benefit in performance to outweigh all the overhead in terms of I have to put this thing on, and there is going to be some amount of discomfort at the interface, right? Sometimes minimal, but something. And you gotta buy it, and you gotta charge it, and all these things. In order to justify all of that overhead, the performance enhancement has to be big. And you see this in some of the prosthetic limb commercial products out there where, the classic example is very fancy upper limb prosthesis. And you talk to the prosthetist and they'll tell you, yeah, those things, people get them and then they sit on the shelf because all that overhead is too much for the small enhancement in performance. But when we get the performance that these devices theoretically could deliver to a person, then I think there's going to be a product that takes off, right? And I think we're there. We've really cracked for ankle exoskeletons, for example. We've cracked it. We've got people walking around campus with a device that's automatically adjusting to their needs and improving their cost of transport by 15% or something. So, and increasing their speed by 10% at the same time. That's pretty good. That's in the neighborhood of things that, say, an older adult might use to get across the street while the light's still on walk or where.
I agree with you entirely that we're there. So don't take this the wrong way, but the old startup sort of cliche is 10 times better or 10 times cheaper, ideally both. So what's the baseline on the ankle exo? What are we comparing to when we make that pitch?
Yeah, I think, if you're 10x, boy, that's great. Or if you're providing some just completely new functionality that people can imagine changing their lives in some way, that's great. But for people, pretty small changes in some of these performance outcomes does influence behavior. So with energy economy, which, as you mentioned, has been something I've spent a lot of time thinking about. There's lots of different important outcomes, but if you're just thinking about energy use, people will change their behavior to save just a few percent in metabolic rate. Like, why do you swing your arms when you walk? It's kind of weird, right? Your arms aren't touching the ground. They don't have any direct benefit, and that is obvious. But it turns out that they have this indirect benefit to your leg muscles by reducing changes in angular momentum of your body about vertical axis, and it saves you about 7% energy cost compared to putting your hands in your pockets. And so just 7%, but everybody is trying to gain that 7%. And people like, Srinivasan have done just this big series of experiments showing all these different ways that people will say, choose a path that curves in just the right way to save a few percent of energy cost. So unconsciously, we're always paying quite close attention to these kinds of outcomes, and clinically meaningful benefits, I think, are on the order of 10%. Now there's, maybe the threshold's higher. Maybe you've got, work out of Elliot Rouse's lab suggesting, people can't perceive the difference reliably until it's higher, like 20%. But, that it could end up being sort of on the high end of the perceptible thresholds, depending on the details of the devices and activities. And whatever it is, I think we're going to hit those barriers really soon if we haven't already.
I find that very convincing. This has been a recurring theme on the podcast. I feel like we, many of us, are yearning for more studies, more collaborations that are in the realm of kind of more decision science. Like how do people choose between different ways of doing things, and what outcomes are they optimizing for? You alluded to this earlier on, the importance of energy efficiency and minimizing metabolic costs, of course, while also acknowledging, the importance of these other factors. I'm curious if you're, in together during my PhD work, we dabbled a bit in kind of collecting a range of outcome measures and kind of comparing and contrasting optimal device selection based on different factors. But since we worked together, you've gotten a lot more clever and automated in the techniques for optimization. I'm curious if you have a vision for sort of multi-outcome simultaneous optimization. Is that something you've been getting involved in?
Oh, sure. Well, we have a paper that's in review right now on simultaneous optimizing speed and energy economy for older adults. And the optimization approach, I think, changes relatively little when you add more terms to the objective function. It's just, I should be careful that depending on the complexity of the landscape and any sort of nonlinear interactions that are introduced, it could take longer to optimize. You might have increased risk of getting stuck in local minima, things like that. But the approach itself is very similar, regardless of what your objective function is, how many terms there are in it. I think a really interesting problem is trying to identify the terms in the objective function that the human nervous system cares about and their weights. And we have some ideas about these things based on intuition and our own experience moving through the world. But I think a data-driven approach to try and identify those costs and weights would be really powerful. And I think that we're getting close to having the capabilities of doing that. So inverse optimization, and there are various ways of doing it, but they generally require a lot more time than optimization, right? You could think of it as one sort of straightforward approach is optimize iteratively to see what's preferred among the different optimized approaches. So you need a lot of data. You need a lot of human robot interaction data, but with these more and more reliable hardware systems, and as we're getting to devices that we might be able to send home with people and collect lots and lots of data, then I think we're going to have the opportunity to answer that question. What is the nervous system trying to accomplish? And a sort of related question there is, what are the constraints that the nervous system might be facing? And that's thorny and very vaguely defined at the moment, but that could prove to be important for understanding, predicting how people respond to these kinds of devices.
Very cool. I think there's a macro level consideration here, which is that in an aging world with a high prevalence of mobility disorders and a seemingly kind of shrinking pool of expert clinicians to make decisions about design and prescription, there is a growing need for automated methods, AI-based methods for assisting with this process. But it's my belief that there's still going to be a very important role for the clinician. Their intuition and their subjective kind of opinions do have value, as well as the subjective impressions of the individual. So I guess maybe there's a dream state where we reverse engineer the human to the point where we don't need to talk about it. We could just see what the computer comes up with. But I think realistically, there's a period of kind of shared decision making where the algorithms are working together with the humans, and maybe the algorithms assist the human in making a decision, or the humans, I don't know, kind of police or guide the algorithm in some way. But yeah, I'm curious what your opinion on that is, how we kind of balance the subjective and objective.
Totally. I agree with that framing. I think in the long term, we probably will be able to automate the process of prescription to a high degree, but we're still in this phase where, again, you need the training data to learn those models, right? So you could learn a model of prosthetist. You learn the model of professor teaching courses in mechanical design, if you have the right data set. And so you need to measure all these very complex factors that might not be so obvious. Like, what is it that the prosthetist is really paying attention to in their patient might be lots of things that some things they might not even be consciously aware of. So you have to start by taking a lot of measurements of the individual. And then some of those measurements might require some form of interaction, right? They might require asking the person to do something. And so that could be an added challenge. And then you need successful prescriptions or device designs to work from. We have a good bit with the standard of care devices. We have a really big set of prescriptions that we could potentially learn from. But with these new devices, robotic devices, we have extremely little data. So it feels to me like this is something where we'd have to make that an active project. We're not going to be passively collecting the data that's needed, probably, because we're not getting the characteristics from patients that we really need yet in some form that's suitable to learning data-driven approaches. And then we need to get to a point where we are having really successful experiences with this new class of devices, and that's decades, right? And then I think it's possible to sidestep the optimization stuff that we're doing and jump straight to the device that the person needs. So, for example, with our ankle exoskeletons, where we've done a lot of work, we can learn a model that does the optimization based just on exoskeleton angles, but we don't have enough data to learn a model of what control settings will be best for this person. And all the characteristics we've looked at to try to predict what will the benefits be or what will the ideal parameters be have not worked. We're just looking at 10, 20 participants. It's just not nearly enough data. And we have also, certainly have not measured all the characteristics of that. So that's a 50-year kind of problem, I think.
Yeah.
But we'll get there eventually.
Interesting. I think as folks engaged in this field, we have to be careful to not frame this as like a binary outcome. Being in Pittsburgh and being a gearhead, I think a lot about cars and the autonomous driving industry, which I'm by no means an expert on, but lots of folks out there that are kind of driving towards fully autonomous vehicles. And there's just so many challenges with this. It doesn't work. It's not practical yet. And yet there are all these aspects of that technology development that are relevant to sort of AI assisted driving, where you have the person and the machine working together. And over the decades of deployment of that technology, you're collecting more and more data. You're enabling, you're working towards that big goal, which may be pretty far out in the distance, but it's still something that kind of can drive the field. I wanted to touch on my view anyway of the data collecting effort, which is that it's much bigger than any one of us. I at Humotech am not going to be able to effectively collect the massive amounts of data to do the things that we want to do alone. Similarly, I mean, in your lab, you're limited. Somehow we all need to kind of work together to kind of pool data and kind of share insights, and then be able to extract value. I have recently become aware of a really interesting effort, which if you haven't heard about it, I suggest looking it up. It's called the Limb Loss Preservation Registry. Limb Loss and Preservation Registry. They are collecting data from the electronic health records of patients who have experienced amputation. So every time that in a participating hospital or clinic, there is an amputation-related kind of entry into the database, the patient record is downloaded and all sorts of demographics and kind of information about the individual and their prosthesis is stored. Anyway, I think it's really exciting to start to see this coalescence, to be talking to people like yourself that are kind of see this future that like we need more data and data is going to unlock all this opportunity, and to also see it happening on the health system side. I think we're headed towards something big.
I totally agree. I had not heard about that effort, but that is fantastic. That's exciting. We have been a few of us at Stanford have been working along similar lines, but for just the general case of gathering biomechanics data to try to learn models of human motor control and adaptation. And so it's called Add Biomechanics, and this is a website you can go to right now. The idea here is that we want high quality motion capture data, ideally with, forces and marker data and muscle activity and everything we can get in a consistent format, so that you start to generate the amount of data that's required to learn these complex models. But of course, sharing data in a consistent format is a lot of overhead, and people just don't do it. There's been lots of ways that you could do that in the past, but it's like, as a busy graduate student, I need to answer these emails. I don't have time to spend a day reformatting everything to fit into the database. So to make this more appealing and attractive, the website does a service for the user. And what it does is it handles the OpenSim scaling and adjustment to make the dynamics consistent for your data set. So what you do is you feed in marker trajectories and forces, and it gives you a scaled OpenSim model and the inverse kinematics and inverse dynamics, which sides it's about a day's worth of work per subject that is done for you automatically in a few minutes by Add Biomechanics. And we're working on enhancing the functionality so it'll do like marker gap filling and labeling and those sorts of things as well, so that the hope is we can dramatically reduce the barrier to collecting motion capture data, make it a lot easier so that people collect a lot more while simultaneously aggregating things into a big database that's publicly accessible, that's all in the same format, so that you can apply AI ML techniques to it.
Geez, I'm jealous of all the PhD students studying today who have access to all these tools.
I know, man. I just the many hours sitting in the basement of the CCRB at Michigan campus, gap filling. Oh my gosh, many a Friday night actually.
For me, it was Ween Hall at Carnegie Mellon. Yeah, that's really cool. I need to learn more about that. I'll get the URL for Add Biomechanics and share it in the show notes.
Right on. And this is work with Karen Liu and Scott Delphin.
All right. Well, we're getting to the end here. I got my two boilerplate questions for folks listening who might be interested in working with you, either as a student in your lab or a collaborator. Can you just share with everyone how to find you online and the best way to contact you?
Oh, sure. Yeah. Our website is biomechatronics.stanford.edu, and I maintain it myself. We've got all of our papers and videos and some, just random photos from lab events and stuff like that. Worth checking out. And I do everything by email, so send me a note if you're interested in collaborating or joining the group. Super.
Yes, I can attest to you having an excellent lab webpage. Thanks for maintaining that. So, finally, I was hoping, Steve, you could share a call to action with our audience.
A call to action. So, how do people? What is the definition of a call to action in this context? Are you talking about particular projects or an approach to research, or what do you have in mind?
I'm intentionally vague here. I'm hoping you can inspire a listener or two or 100. I don't know how many listeners we have to go out and do something differently now that they've listened to this podcast.
I would say, I guess I can speak to people that maybe are on a similar journey to myself. I started out as a mechanical engineer, really focused on robotics and mechanical systems. And when I shifted to devices that interact with humans, I thought of the human as a robot. And it's sort of embarrassing to say it that simply and straightforwardly, but I think secretly a lot of us do think about the human being as this mechanical system. And of course, in some ways that analogy is apt. We're all subject to Newton's laws of motion and everything. But in many important ways, we're just very different from robots in the way that our muscles work, and especially in the way that our nervous system works to coordinate our motions. And I think I implore those working on these kinds of devices to accept that the human is so complicated that your intuition about how they work is wrong, probably, and and not to drive projects and spend years working based on a guess as to what people want, but get to experiments with people as fast as possible and really learn from those human users as much as possible, as early as possible, to guide your project. Because I think that is just, it's essential for developing devices that actually deliver functional benefits to people. And also, working with people to find out what those functional benefits are that they need, and to take a systematic approach to this. I have these, I've been promoting these tools and methods, but any kind of systematic approach that thoughtfully reflects this central challenge is welcome and needed, and likely to lead to the kinds of big advancements and breakthroughs that we really need as a field to get to that cost benefit balance that is necessary for these products to really gain commercial success and thereby be used by people to improve their lives.
I love that advice, Steve. Thank you. I think we could all stand to spend more time just being friends, allies to the people we're intending to benefit. With that, that's the end. Thanks everyone for listening.